8 o'clock. Welcome all. This is show 12. Okay, the 12th show. We have 6 panelists. We have Chris, we have Ivan, we have Alex, we have Evan, we have David, and myself. And we again prepare for 2 relatively easier questions and 1 quite difficult question. And Ivan will share with us the first one, right? That's a easier number sense question.
And it's easy to guess it was given in 2004. So we have 2 arithmetic sequences, 1, 4, dot, dot, dot. So I guess it will be what, 7, 10, and so on. The other one, 9, 16, 23, and so on. The set S is the union of the first 2004 terms of each sequence. How many distinct numbers are in S?
Yeah. Do you want to do any polls?
Well, let's see who proposed it.
Okay.
Or where it was proposed. It's 2 good questions. Let's see where it was proposed. EMCC is the Exeter Math Club competitions, if some people don't know about it.
So that should not be an answer because EMCC doesn't even start in 2004.
When did you guys start it to run it? 2011?
I think it's somewhere in 2008.
You could still run that problem in like 2020. Just put 2004. Hey, we've had this on the shelf for 16 years, you know.
Okay, almost 80% voted, so I'll end the poll there.
Yeah, it is on AMC, right? So Ivan, you want to start how to solve this thing? I think basically this problem is telling students a little bit number sense and also understand the definition of set, right? Basically, in a set, we don't allow what? A number to repeat. So if the sum numbers appeared in both sequence, they, that's why it's not, if you combine the 2004 together, it's not 4008 because some of the number repeats. So basically we need to figure out how many repeating numbers, right?
Okay, but wait, if it's 1, 4, I go up every 3, right?
Yeah.
So 2004th term will be equal to 1 plus 3 times 2003. Am I going the right direction?
Yeah.
And then I have the other sequence, 9, 16, 23. The difference is 7. So 9 plus 7 times 2003. These are 2, let's say, sequences I have, or sets A and B. I can think of them.
Right. So we want to take out all the repeating numbers, right? Then we'll be done. So what's the first repeating number?
16.
16, right? Because if we write a few, we will get 16, right?
16, yeah. 16 is the, so we want to find their intersection. The first one is 16, yes.
Yeah. And then after that, then what? This number goes every time by 3, and the second one goes every time by what? By 7, right?
So 16 plus 21.
Yeah, so that's their least common multiple.
I found it interesting that one of the choices, it was actually choice E, was 4007. So I'm not sure what the thinking was. Maybe if you list out a few terms and you say, oh, I found 16, so I got to subtract 1.
Yeah. Well, because the next number is quite large, right?
Right,
37.
right.
You have to take quite a while to get there.
Right. Run out of patience.
Yeah.
Okay,
So basically, those are the numbers that repeats. So we should just go to set A because set B have bigger numbers, right? Yeah.
so I need to know how many multiples of 7 are in 2003.
Yeah, you basically want a 16 plus what? 7K is less than what? This 1 plus what?
Is less than
A 21K or 21A or whatever. Yeah, you need a variable, right?
Yeah.
1 plus 3 times 2003. Okay.
Yeah.
And then you have an estimate for K, right?
Right.
Which is 3 times 2003 minus 15 divided by 16,
What are you
21.
doing? Yeah.
21K. K is less than this. So
Right.
I can factor out 3. So
Make that equal less than.
less than or equal to, right? 2003 minus 5 divided by 7, which is 1998 divided by 7, which is what?
2.
7.
No, not that big, right? 27?
2, sorry, 1459 is what? 8?
8.
Well, 2002 is a multiple of 7.
Yeah. 280.
285?
Yeah.
285 and plus
A little
something.
bit. Right. Some remainder, right? So we can go at, so basically there are 285 repeating numbers, right?
Including 16, it's going to be 286, right? So the last one that will repeat is 16 plus 21 times 285.
Yeah.
So there are 286 repeating numbers. So A intersection with B will have 286 numbers.
Yeah.
We need to know how many numbers in their union. Well, it's A plus B minus their intersection.
Yeah.
I don't know how you guys can compute.
So here comes our warm up, right? So we are done with this one, right? It's just a little bit, number sensing for fun.
Okay, guys. What's the next problem? I think it's right over here.
You're saving paper.
Yeah, I'm saving paper, yes. So it's a geometry, and I have the diagram over here, so you guys even can read the problem and follow it. So, David, maybe you can read the problem.
All right, sure. In triangle Leo, point J lies on segment LO, so that JE is perpendicular to EO, and point S lies on segment LE, so that JS is perpendicular to LE. Given that JS equals 9, EO equals 20, and JO plus SE equals 37, find the perimeter of triangle Leo.
Yeah, you want to do a poll on author or contest
let's
or whatever
see.
year, whatever you want.
Let's see who's the author. Will the audience guess? Wait, do we have more attendees? Do we need someone? I feel the voting is totally random. Okay, so 81% voted. So majority. You guys didn't guess. It's not David and it's not Yannick.
It's actually Chris, right?
Yep.
Okay. I think Chris, you wrote this problem in memory of Leo Schneider.
Yes, indeed, I did. Sadly, several hours after ARML 2010, after Leo won the highest award at ARML for contributions, he passed away suddenly. And some of you who've done ARML know about the super relay. I've been the principal author of that since 2000. And ever since Leo's passing, like from 2011 to the present day, I always work in a Leo problem. And we've even had a few Leo kind of Easter eggs embedded in ARML problems. So Leo J. Schneider, that's where the J and the S come from. So yeah.
And if people haven't, well, if our people are older like I do, then I learned my math back then in the 80s by doing the old Ashby, right? And Leo was the chair for that committee for a long time.
Yeah, I think he was 89 to 94, and he wrote one of the compilation books. So yeah.
And I also want to say, when I was solving this problem in my head, I made some very silly mistakes, because somehow I think SJOE is a trapezoid, because I didn't mark 90 degrees very carefully. I thought there are two 90 degrees, but one of them actually only stopped at a J. JE didn't go to SE, you know?
Yeah. I think part of the key, and again, I don't know exactly what possessed me to come up with this configuration, or the condition of JO plus SE equals 37, which is sort of unusual. But I think part of the key is just getting the right diagram. And after you read the first clause, I think it's helpful to draw a right triangle JOE.
Yeah.
And then you extend, what is it?
Well, you see, you have lots of right triangles, right? So clearly you want to set up some kind of Pythagorean theorems.
Yeah. Oh, well, yeah, once you've gotten a triangle JOE drawn, then it seems to make sense that you extend OJ past J to the point L, and then you find that triangle LEO, or angle LEO, is obtuse, so that you have the right picture.
Yeah.
Well, I agree with Zooming that you have to work with Pythagorean theorems.
Yep.
And this condition tells you like one of them is x and the other one is 37 minus x. So what can you do? JE you express in terms of x. And then you can find x.
Yeah.
Pretty much from Pythagorean theorem in the GEO. So 9 squared plus x squared plus 20 squared will be 37 minus x all squared. But this doesn't solve the problem. That's the most...
Well, at least you can get x now, right?
Yeah, x is equal to, I think it's 12 if you solve it.
Yeah, it's 12.
Yeah. Okay, it's 12.
So pretty coincidentally, those two triangles are similar, though. That makes your life a little easier, but not significantly.
Wait. This is 12, which means this one is
15. It's a 9, 12, 15.
15. Okay. And the bottom is 25. Okay.
Yeah. So I don't know the better way to finish, but and I haven't done the computation, but you can finish by computing. So you know that angle LJS is equal to 180 degrees minus 2 times, well, whatever that common angle SJE equals EJO is. They're both 3, 4, 5s.
So you can mark those are thetas. You can mark those are two thetas, right?
Yeah, so you can finish by tangent angle identity. That will get you the tangent of the left angle, and then you're basically done.
Wait,
I don't know the faster way to do it. Yeah.
Huh. And you want to find what? LS and LJ, right?
Yeah.
And so this is 180 minus 2 theta. Okay.
Yep.
So you will find what? Tangent of that angle?
Yeah, I'm just going to do tangent because that's like the tangent angle identity is a one variable identity as opposed to the sines and cosines, which are like 4 variables.
So let's remind our students. Tangent of 180 minus 2 theta is equal to what? In terms of
well, that should be negative tangent of theta, negative tangent of 2 theta, I believe.
Okay. And how do you compute tangent of theta in terms of theta?
Well, that's equal to negative 2 times tan theta over 1 minus. Your paper is a little bit on the low side. Over 1 minus tan squared theta, and now it's just a computation.
Oh, nice. You know tangent of that angle, you know one of the sides is 9, you can find LS, and
Yep.
then you can find LJ.
Yes. Yep.
Oh, that's cool. Nice.
Fairly certain this is if I remember correctly, I think you end up getting that LSJ as a 27, 24, 25. I'm not.
Yes, you do.
Yeah, I remember. It's sort of weird that if you take like the angle, the smaller angle of a 345, and you double it, you get like an angle, or you get an angle of a 7, 24, 25, which is kind of neat.
Yep.
So 7, 24, 25. And you cut it in half, or no?
Yeah.
Move the paper up a little. Yeah. Yeah. In my solution, I used the double angle identity for sine. Either way.
Oh, basically,
yeah.
Anything you do will work because it's double angle, right?
Yeah. Yeah.
There's also an angle bisector theorem, right? I forgot what it was, but I mean, JE is an angle bisector of triangle LSJ.
That's true. Angle bisector theorem for external angle bisectors is the same as the internal one because you can form a harmonic division in like the relevant points.
David, or you if you just know that fact, you don't need to.
Yeah, that seems a little. That is a good way to remember it. I'll give you that.
So GE, if you take this triangle, GE is the external angle bisector.
Right. At least we should let the students know this, right? Interior and exterior, they have exactly the same structure, right?
Yes.
Ratio.
So, okay, so if this is Y, it means what? SE over LE, which is 12 over 12 plus Y, should be the same as SJ over LJ, which is 9 over 9 squared plus Y squared, right? And you can solve for Y.
Yeah.
Okay.
So 2 comments from me, the proposer. One is that, yeah, now that David mentions it, yeah, it is somewhat of, I suppose, a coincidence that these happen to be similar triangles. I intentionally did this because I did want it to basically devolve into a double angle identity, and reward people for recognizing, oh, hey, 9, 12, 15, 15, 20, 25. The second thing is, you don't actually, so we have JO plus SE, we are given EO, and so to find the perimeter, we really have to find LJ plus LS. And what I like is that once you recognize that LJS is similar to a 7, 24, 25, you don't actually have to explicitly solve for LS and LJ, so that if 9 represents, let's say, 7 Z, then LS is 24Z, and LJ is 25Z, and the sum of those two is 49Z, which is just 7 times 7Z, but we know what 7Z is.
7 times 7Z, which is 7 times 9, 63. Yeah. Oh, nice shortcut.
Yeah.
Okay. Cool.
It's also worth noting that like making that thing a double angle does reduce the amount of computation needed, which is good because like the point of this problem is not to do the computation. So
right.
I do like that about this problem.
Yeah.
Yeah, we didn't talk about where it came from. It was actually an ARML individual problem, and I modified the wording just slightly for this show, just in case we were going to ask about it, because many who have done ARML know that most of the problems, they say the word compute. So I changed compute to find just to throw people off a little bit. But it was a individual number 6, so kind of getting into the medium level of difficulty. And yes, I didn't want it to be that computationally intensive as much as, if you see some of these relationships, that you'd be home free.
Good. So we will move on to the harder one, right? Harder one is a scary inequality. Let's see what it is look like.
Inequalities are never scary, right?
Only 4 variables, not that much.
It scared me.
4 is greater than 3.
Wait, it's an equality, right? Oh, well, maximum. Maximum, yeah.
Ivan, can you give me screen sharing? I seem to be unable to share for some reason.
Sure, yes, 1 second. I always forget to change that.
If I were at the IMO still voting, I would definitely vote for this kind of question. Because of what? Currently, I feel like students don't want to do inequality anymore. But every once in a while, we should come back to visit. Because currently, all the popular problems are functional equation. You know, make me so dizzy. Always compute F0, F1, and you know, 1-to-1 bijection. Oh,
I mean, to be fair, I'm pretty sure people were saying the same thing about inequalities. Probably.
Yeah, so that's why every
in
once
the
in a
old
while you need to
days.
recycle it back, right? Now you look at this. This is not the same technique as Ivan were doing 12 years ago, right? 15 years ago, Ivan preparing for our IMO spent a lot of time working on what? Inequalities. Now they don't.
Okay, let's see if that works.
I'd rather see polynomials come back. I think polynomials is an algebra subject that is.
So anything but functional equations.
No, functionals are fine if they have seen meaning behind them. If you see that they're related, or they hide some relation, for a cubic or for something. There were a few really nice functions.
Inequalities in functional equations are relatively easy to write. Like functional equations, there's this joke that like you can just take a thing that you know is true and slap a bunch of f's on it, and then boom, you've got yourself a functional equation. Whether or not that functional equation is good is another story, but I mean that's the same thing with every single problem. And inequalities, I don't know. You could probably come up with something symmetric and hope to God that everything works out, but I still think that like with polynomials you have a lot more structure to worry about, so things end up being a little more difficult.
I mean, you say that as a joke about functional equations. I'm pretty sure it's not a joke.
Oh, I'm not saying it's a joke. I'm saying like,
you know, what's the issue when you teach? What's the only difference when you teach inequality and the functional equation? They are all kind of like manipulation and the techniques, right? When you teach inequality, at least by first look, you know those inequality looks different. But when you teach functional equations, when you look at a whole page of 12, 15 problems, by the first glance, you feel like all of them are the same. Because that functional identity, nobody knows immediately what's their difference, you know?
Yeah.
Well, let's see.
All right. So let me see what I want to say about this. Yeah, okay. So I guess the first thing I want to say about this problem is what the numerical answer is, because normally when you see it like an inequality like this, the first thing you try is, okay, what if I just set all the variables equal to each other? So in this case, you might try A equals B equals C equals D is 25. And this gives some value, whatever it is. So 4 times the cube root of 25 over 32. And there's going to be a bunch of cube roots, and I don't really want to. Do I want to put them? I'm going to put the 4 into the cube root just so that it's easier to see what's going on, because we want to like compare the values of s across different choices. And if I have something like 4 cube root 25 over 32, it'll be very hard to see what's going on. So I'm just going to put that in. It's actually cube root of 50. And okay, are there any ABCD that can do better than that?
Okay, I originally tried, this is why I think this problem is so sneaky, because the 3 cases I tried, none of them hit the actual value. I tried 50 zeros and I tried hundreds.
Yeah, so if you get 50, 0, 50, 0, what do you get?
You get something nasty.
It's 2 cube root 50 over 7.
Yeah.
And then you also know that this thing is only cyclically what? Symmetric, right?
Oh, yeah, so I guess I do kind of want
It
to
doesn't
try.
really give you everything. So, maybe it is. Yeah.
That is, I mean, or you've got something that's slightly larger than root 50 because you cube root of 50 if you take the 2 into the inside.
Yeah, and this is why I'm keeping the 2 on the, yeah, I'm putting them all inside because otherwise you can't really tell. In fact, I'm going to write this as cube root of, we're going to do, I think people call these mixed numbers or something. I'll write it this way so you can actually see what's inside. It's like 57 plus 1/7. So
Yeah.
you can already do better than the all equal case, which is kind of scary. And then the other cases you should at some point try are, I think, 50, 50, 0, 0, and then also setting them, one of them to 100 and the rest to 0.
Yeah.
So this will give you something. Someone help me out and compute these because I didn't compute them beforehand.
Cube root of 50 over 57 plus cube root of 57 over 50 over 7 plus 2 zeros.
Oh geez. Okay. So
Yeah.
it's 50.
Well,
Well, the second one is, the third one is definitely worse than the second one, right? Because yeah, this is less than previous. So we won't worry about that. And then in the last case, if I do this, I get s equals cube root 100 over 7. So that's actually like, yeah. So far the thing that looks closest is 50, 0, 50, 0. Of like the 4 obvious cases to try. Yeah. Can I run with this?
And after that, I waste all lots of time trying to smooth everything to this thing, and then I realize it's not that thing.
Yeah.
Made me not happy.
Yeah, I guess in order for this discussion to make sense, I do actually have to give the answer away, which is that 7 there isn't a random 7. There's a, if A, B, C, D is 49, 1, 49, 1, then in that case you get S is equal to, okay, so this one I should know because it's the correct answer, but I don't remember what it is. Cube root of 512 over 7? There we go. Yeah. That's not the correct law tech. And so now you can see why the 7 is there. The 7 to 100 are kind of chosen to kind of not give away that this is the actual answer. It's actually like quite a bit bigger. Okay, so in order to tell the story of how I came up with this problem, I need to talk about something which is, these days I think people often call it tangent line trick. The idea is that, actually this will work better if I give an actual example. So I'm gonna pull a problem from some random contest. This is Elmo Shortlist 2013.
Or you pick all those 2006, 2007 MOs in AOP, you can find almost every year there's one tangent line problem,
2006?
That's the hot topic back then.
Evan, the latest one was USAMO 2000, number
17.
6.
Oh, right, yeah.
Numbers.
That is, I thought about using the 2017 problem, but I think it's too tricky. Like, cause it's actually two mixed variables mixed together. Is there another one I can? Okay, let me just stick with the one that I have prepared so I don't confuse myself. So this is a problem that says if ABC is non-negative and A plus B plus C equals 3, then you want to show some random thing like, okay, let me make sure I get this right because I'm quoting a problem. Yeah. Okay, so it's the cyclic sum of 18, 3 minus a, 4 minus a. Let me just do it this way. Minus a plus a squared should be greater than or equal to 6. Then that's definitely wrong. What's the constant supposed to be? 2, 6, 6g is 21? Right hand side's not 6, it should be 21. Wait, why is it minus? Oh, yeah, it's minus. Okay, that's why I'm confused. Okay, and basically the premise is when I see an inequality that's of this shape, one of the first things you might hope is that, okay, maybe like you can just use Jensen on it because this whole thing in the brackets is some function of, it's not 6, it's 15. That's wrong in my notes. This whole thing is some function of a. So you might hope that this function is convex, but unfortunately it isn't. If you draw what the graph of this thing looks like, it looks something like this. So this is what the function y equals 18 over 3 minus x, 4 minus x, minus x squared is. That's what the graph looks like. And my whiteboard is not behaving. Where'd you go? Ah, geez, one moment, please. There we go. So that's what the graph looks like. So it's not convex, and if you try to use Jensen, it doesn't work. What the tangent line trick does is like, okay, well, I think my equality case is when all the variables are equal to 1. And so what I tried to do instead is, this picture is really far off. Let me put one around here. You draw this tangent line to the graph at x equals 1. And if the function lies above it, then you get an inequality that will help you out anyways. What happens in this particular problem is that you get, if you take the tangent line at 1, you get that this thing turns out to be always at least x plus 3 over 2. So y equals x plus 3 halves is the tangent line. And the graph of the function just happens to always lie above that line.
A plus 3 over 2, right?
Sorry?
A plus 3 over 2.
Just the x should be an A.
E. Yeah, okay. X should be an A. Okay, wait, why are my constants all off? 3, 2, sorry, but I don't know why I can't do arithmetic when I'm on camera. This should be a 6. So this inequality turns out to be true, and then that kind of solves the problem. So that's the premise of the tangent line trick. It's like if you want to use Jensen, but the function is not convex, you can draw the tangent at the point you care about instead, and then cross your fingers that the graph will lie entirely above the line. And if so, then you're okay. Okay, so why is that relevant to this problem? Well, the way I came up with this problem is this trick was popular. I guess Zooming said it was popular around like 2006 or 7. I came up just as this trick was starting to die out. So I saw this, like, oh, this is pretty cool. I can, solve problems by taking a tangent line. Is there some way that I can try to take, rather than just a tangent line, a tangent parabola instead?
Mm-hmm.
So what does that even mean? You'd want to, rather than take the line approximating, you want to take what would be, if you know calculus, is like a second order Taylor approximation. So rather than a line, you'd bound it above by a parabola, and you can try to do something like that. What I mean by this is I could try to think about, say, if f of x was bounded above by some quadratic, ax squared plus bx plus c, then I could add them up and do something with it. Okay, well, if I'm willing to do something like this, then I can actually make the parabola touch my graph at 2 points. And so the idea that I had when I started the problem was I looked at this thing, x minus 1 squared, x minus 7 squared over, I want to pick a denominator of x squared plus 7. I'll explain why in a moment. If you take this thing and you expand it, you'll get something, and I didn't prepare in advance, so I don't know what it is off my head. wolframalpha.com. But one of my notes is different, so I'm sort of boxing myself into a corner. My notes say 2 instead of 7. Wait, that's not supposed to happen. Oh,
What does it look like?
something's wrong. Why is there a set? Oh, I see. No. Wait, what? Okay. I think maybe I want this instead. What I wanted to say was that you're going to get like a quadratic thing, which would be, I guess, x squared. That's not any better. No, just do the division. Okay, I'm going to assume. No, wait, that's not even the right order. Okay, I think this is what it should be. And then I want it to be Suchi. All right, what's the constant term? 497, 49, 448. Good enough.
And
Okay.
you can forget about the remainder because it's...
Yeah. So anyways, what I did was I started with this. And this is an inequality where, I mean, because it's a square, it's going to be always non-negative. And so I realized if I rearrange this, then what I get is the inequality 448 over x squared plus 7 is less than or equal to x squared minus 16x plus 71 for every x. And so what that means is if I had some variables and I knew the sum of the variables and I knew the sum of the squares of the variables, then you can get sum bound automatically on like this 1 over x squared plus thing. I see a question in the Q&A that says, how do you know 49.1, 49.1 is optimal? The mathematical answer is you don't know for sure until you've proved it. That's sort of like the issue with these kind of things. The practical answer is the numbers work out so nicely that it had to be rigged. I think if you try the 49, 49.1 and you see it's better than all 4 of the normal cases, and like the square just kind of, 49 and 1 is 50 and that makes 100, you kind of know the proposer put that there. Like it's kind of set up that way.
I mean, I'd also add that like when I tried this problem, it's also somewhat natural to try something like a comma b comma c comma d equals x y x y, and then you get that's a one variable inequality which you can solve for. You can see that x is maximized when x is 49 or 1, but that's like sort of a leap of faith still because you're assuming that the equality case is x y x y.
Right.
I see. Yeah. Oh, that's actually a good thing to do. Okay, so what does that mean? Okay, so I'm like, great, I have a way where if I tell you the sum and the sum of squares, then I can, come up with this contrived inequality that will have equality cases at 1 and 7. So I wanted to try to hide this in some way. And my idea was, okay, well, maybe I can try to use some Holder inequality. So what does Holder look like? Holder tells me that
there is some sign, I think.
There's a sign there. Yeah, I just noticed. That's the maximum. Okay, what did I do this time? This is 497. So this one here is a minus sign. I'm really not good. This is a minus.
Okay.
Okay, so then we're fine.
Mm-hmm.
Okay, so what does Holder say? Holder says that I can like, if I have my 1 over x squared plus 7, which is the main object right now, then what I can do is I can try to introduce, well, in this problem, I'm interested in sum of x and sum of x squared. So there's 2 things I can write. One is that I can write sum of x, and the other is I can like put a sum of x squared here. So I'm going to go with sum of x because the other case doesn't do anything interesting. And when I do this, you get like this is less than or equal to like something, blah, blah, blah. Yeah, I guess it's like cube root x over x squared plus 7 or something like that. Doesn't really matter. You can at this point kind of see. Did I mess up
X
again?
squared over x squared.
Yeah, it should be x squared. Okay, so you can start to see where this problem's coming from. And if I want to make this look like the original problem, I better actually change the order of this. So rather than cyclic sum of x, I can put a cyclic sum of w here. I'm doing 18 minutes. So now this is like kind of starting to look like a problem. So you can look now here and you're like, okay, well, what can I do with this? So on the left-hand side, we know this guy is less than or equal to, I guess it's like 288, some constant, minus 16 times the sum of x, and then
Your
plus the
screen's a
sum
little low.
all right. Let me zoom out a little. So minus 16 times the sum and then times the sum squared. And then this guy is equal to sum of x all squared. And so I was like, okay, well, again, if I told you what the sum of the x was and the sum of the x squared was, you would get some number as a bound here. But I was curious, okay, well, I mean, maybe I have this sum of x and I can just kind of try to get rid of it. And what would be the best sum x in order to get rid of it? So by AMGM, what that means is I'm going to write this sum of x as, let me do this in a different color, 8 sum of x, 8 sum of x times 1 over 64. And by AMGM, because these guys have fixed sum, once I fix the sum of the squares, I just want them to be equal. So you would want 288 minus 16 sum plus sum of x squared is 8 sum of x. And if I fix this guy to be my 100, then you would want.
Evan, don't you want 284?
Did I mismultiply? This is why I need to prepare in advance. Oh my gosh. 284. Okay, so if I make that my 100, then I want 384 is equal to 24 sum of x minus 100 here. So the best value for sum of x is really? Okay, 288 did the right thing. Why is this not doing the right thing?
No, you don't
No,
have.
oh no, it's 16. We're fine. 16. 284 over 24 is. What did I do?
You just have 284 plus 100 is 384 on the left hand side.
Oh,
right?
okay, right. 384. There we go. This is what happens when I don't prepare. All right, so I looked at this. Okay, well, that's fine. And then I realized that the sum of 16 is actually the right thing that you get. It's like, oh wait, this is actually the thing that happens with 7171. So this was like, I looked at this and like, wait, really? Like this can't be right. And I checked it again. I'm like, oh no, it is actually right. And the big surprise in this problem was because originally I was just trying to say, I'm going to tell you the sum of x and the sum of x squared, and I want to pick a value of sum of x that will work pretty well. But somehow it turns out when I do this holder, the optimum case lines up exactly in the right way. It's like, okay, when you do the AMGM, you find that I want the sum of x to be 16, which it will be anyways, in order for the sum of x squared to be 100. So I hit this coincidence, like, why is this happening? And I couldn't figure it out, but I had this problem, so I sent it into the IMO. And the IMO problem selection committee works on it, and I don't know what they thought of it. So at the IMO, the problem selection committee runs their own internal beauty contest where they argue about how nice they think the problems are. And half the committee gave this problem the lowest possible rating. The other half it gave it the highest possible rating. So I kind of looked at it, I was like, well, okay, fine. But I also was more interested in like the solution that they came up with. And the idea behind their solution was, okay, well, they know the equality case is 149 because they either guessed it or, like Alex said, they do some calculus optimization and realize that this point's very important. So what they did was like, okay, sort the variables w, x, y, z, and that's completely off screen. Where did I put it? Okay. You sort the variables w, x, y, z, and then by rearrangement.
Wait, Evan, a w squared is a? What's the?
It's a different w. Sorry. So in the previous stuff, the x squared is y.
X squared
The
was
squares are the
a.
variables. Here,
Yes.
they're. I'll just use different letters. How about that? No, it's less confusing that way.
Ivan, they just relabel this A, B, C, D. Basically, they are saying any four variable, what will happen? Yeah.
Yeah. So I'm going to sort them, and by the rearrangement inequality, you get p over s plus 7 plus cube root q over s is less than or equal to this. And you might be a little worried initially because you're like, wait, I thought this inequality was cyclic. Like, how come you can do this? But if you think about it, the rearrangement is okay no matter what, because what I say is, okay, just sort the variables in some order. I don't care if it's the same order cyclically or not. Then when I split the fractions in the obvious way, the smallest one is p, the largest one is s. So this is the this will be the maximal term, and this will be like kind of the minimal term, sort of no matter what the original order was. But something happens when you do this rearrangement inequality. You look at this like, wait, oh, now Q and R don't talk to each other, P and S don't talk to each other. So what sort of happens is you suddenly turn it into a two-variable version of the problem, where here's like this cube root and there's the other cube root. And so we would be done if we can solve the two-variable version and show that you want, in this case, we think the equality case is 1, 1, 49, 49. So it would be sufficient to show, where's my notes? Claim cube root of P over, I'll use P and S. This one is optimized at something like this. I think this is the exact form that you want. It's not showing. So this is roughly the thing that says this is the two-variable version of the problem. But the right-hand side, you have to contrive a little. And you can prove this by using holder. Oh, do I want to try to do that now? I'll show you guys a holder. Why not? We have a bit of time. So the proof goes, well, I told you that I wanted holders, so this is what I'm going to do. I'm going to take P plus 7 here, and 7 plus S here, and the main thing I wanted, which is this, I'll just do it this way. P plus 7 plus S plus 7. If I apply holder, this whole thing will be at least the cube of, okay, and then some cube roots job. So this is 7p plus 7 plus cube root of 7s plus 7.
Evan, can you please move?
No. See, because I'm writing this on my iPad, so. Okay.
Yep.
Yeah, and then when you divide through by 7p plus 7s plus 7, this will actually give you exactly the main claim. So very long story short is that the other way you can approach the problem once I give you this statement, if you don't see the work that I put into building it, is you're like, okay, I apply the rearrangement inequality and suddenly I get a two-variable version of the problem. And if you have the two variable version of the problem, then it turns out to be a single application of holder. So anyways, that was the solution the IMO came up with. And then the jury does their thing at the IMO. They vote on the problems. The problem doesn't make it. So I'm like, okay, well, that's fine. I honestly thought this problem might be too hard anyway. So I'm like not that upset that it wasn't chosen. I was like, I thought this result was cool, so I wanted to have it somewhere, but I thought it might not be good if it actually showed up at the IMO, because not that many people would solve it. But then some time passes, and around, I want to say it was around February or March or something, I get an email from Ilya Bogdanov, who is one of the very long-time members of many IMO problem selection committees. And he told me, hey, so you know your inequality from the IMO shortlist. Well, we used it on our Russian TST, and nobody solved it. And also, the organizers came up with this solution. You got to see this. And they told me, this is what you do. You take cube root of a over b plus 7, and you use AMGM. And by AMGM, we're going to say this is less than or equal to 1/3 of the following thing. It's a plus 7 over 64 plus a over a plus 7 plus 7 over b plus 7. Like that. Because, oh, wait, I'm missing a 64 somewhere. Okay, let me just multiply by some constants. 764. I'll do it this way. We'll put the constants here. 7 over 64. Because, well, when I multiply, that's what AMGM says. Like the product of these three guys will give you this stuff on the cube root. And then you add them up cyclically. And you get cube root over 7 over 2 times s is less than or equal to the cyclic sum of the right-hand side. So what happens on the right-hand side? These guys sort of just pair up, and they give you a bunch of 1s. And then the other thing here is a plus 7 over 64. But because you know the sum of the a's, this is also a constant. So this just gives you 10/3. And then that's it. 28. I definitely messed the constants up, but let me just know.
Plus 4 instead of plus 8?
Should be plus 4 instead of, oh yeah, that's why it's not working out. Okay, so this one's a 4. The a plus 64, so you get 100, this is just 2. So this whole thing is equal to 2. Yeah. And so that's the one-line solution. And how they found that, I still haven't actually figured out. But if you piece it together, this happens to work out exactly right. Yeah. And so those are sort of like the three primary solutions I know to this problem. Of course, you can try to do smoothing once you know the answers at 149, 149. But it's a little more involved, I think, than any of these approaches. But the one-line AMGM is just like, somehow someone found this.
Nice.
Alex, in your approach, can you start to do some reasoning to make sure to go to XY case?
No, I mean, I think I just like guessed the answer, and then I tried to do like just like very calculus heavy smoothing.
I see.
Because the problem is like if you just isolate one variable, right? Like it affects two expressions, and it affects them like very unpredictably depending on like, say if you try to move C, it affects like the two middle expressions depending on like what B and D are. So it's hard to use just like monotone arguments there.
It's really cool, yeah.
Yeah.
But I
Mm-hmm.
still think that moving away from inequalities was a good idea.
I don't know, maybe it's a functional equation. See, because with inequalities, like the expressions are artificial in some ways, but at least there's a sense in which I can have a notion that things are like large or small or big or large or small, or like inequalities are sharp in certain ways. Like at least when an inequality, if I see a cubed plus b cubed plus c cubed, I know that's bigger, like a lot bigger than ABC for some definition of a lot. Like it's a lot bigger than ABC. But I always struggle with functional equations because I just don't have any intuition of this form. Like everything I see is just like an equation, and there's no notion of like size or natural interpretation for a lot of them. So it makes it really hard for me because I usually that's the things I rely on a lot for, I guess, Olympia problems in general.
Well, this final AMGM solution is really nice, right?
It's
Look
so
at
short.
how we added it up, right?
Somehow, yeah.
Very cool.